All right, periodic trend video, it's Ms. Butler. Last part, we're going to cover two more trends, electronegativity and electron affinity. So same idea with both these trends. We want to be able to define them, compare for two elements, what has higher or lower, electronegativity and electron affinity, and then being able to know the patterns on the periodic table and be able to explain why. So just a reminder why we're doing this. It's tedious and unnecessary a lot of the time to look up detailed information about different elements because the periodic table has patterns and patterns to help us predict some of the properties that we might see or the characteristics of certain elements. So this video we're going to cover two different trends. One's called electronegativity and the other is called electron affinity. Okay. Electronegativity is a big one. If you're going to remember any of the trends, this is the one to remember because you will see it next unit as well. But it's the atom's ability to attract shared electrons in a chemical bond. So basically what's happening is we now have two different atoms bonded together, and we are measuring one of the atoms, how much it pulls those electrons that are shared, because we know a chemical bond forms between electrons that are shared. Okay, so when I say that something has a high electronegativity, I'm talking about that atom pulling those shared electrons towards itself. A low electronegativity is an atom not pulling those shared electrons towards itself. This trend's important because it basically lets us know how things will react. If something has a high electronegativity, it's going to really want to react and bond to get some shared electrons. All right, so growing up when I was little, well, I have a brother. I was going to say I had a brother. I still have a brother, a little brother named Blake. He's only 15 months younger, though, so we were basically, very close in age growing up, so we had a lot of the same toys, a lot of the same friends. And so one year for Christmas, and this kind of shows you how old I am, our last gift that we opened up from my parents under the tree was a Razor scooter. Not a Razor scooter for me and a Razor scooter for Blake, one Razor scooter. They were the brand new thing. They cost like $300 at the time. It was like the coolest toy. Everyone wanted a Razor scooter under their Christmas tree. They were brand new. And so obviously that's a very expensive gift, so we got one to share between me and Blake. So I want you to picture, we opened this gift, and I want you to picture that Razor scooter going around, Blake riding the Razor scooter around, and me riding that Razor scooter around. And so what happens is we had to share that scooter. Well, I, being the older bossy sister, was more electronegative. So the reality is that this Razor scooter spent much more time near me. I was riding the scooter a lot more than my brother, okay? And then what would happen is my mom would stick her head out the window, and I'd be like, oh, here you go, Blake, and let him ride the scooter, only when my mom was looking. So because I hogged the scooter, it was shared. Technically, we both own the scooter, but since I got to ride it more, I had a higher electronegativity. All right, here are the patterns. So as we go from left to right across a period, electronegativity tends to increase. So let's look at those. Across a period is right here. So basically we're going to be using the same idea. So if I'm looking across the periodic table, we're going this way. These guys are in the same period. They have 3 rings. They have same principal quantum number 3. As we move over, we keep adding protons, which means we have higher Coulombic attraction, right? A bigger magnet in the middle, more muscle in the middle. What this means is that the shared electrons are pulled closer to the nucleus, which makes it smaller, and it's easier then for that nucleus to attract the shared electrons. So I want you to picture 2 atoms sharing their electrons. There's the nucleus. Here's some shared electrons. There's some that just belong to the individual. If I have more protons in my nucleus, I can have a stronger attraction to those shared electrons. Okay. The other thing that sometimes some teachers will talk about is that, remember, we want that magic number 8 for 8 valence electrons. Well, some teachers will discuss, and it's an appropriate argument, that as we get closer to that magic number 8, right? Say like I have 7 valence electrons. I am desperate to get one more, right? I am probably more desperate because I'm only 1 electron away than maybe someone with 5 valence electrons. So it's talking about getting that full octet. One thing that's important, though, is the electronegativity patterns don't work very good for transition metals. So just the pattern is a little more sporadic, and the main part is it does not apply for noble gases. The noble gases, we say, don't really have an electronegativity because what electronegativity is shared electrons. Well, remember, the noble gases already have 8 valence electrons. They don't want to share with anybody. The only elements that are going to share are ones that are very close to that 8, right? So maybe, hey, I'll share with you, you share with me, so we both have 8 electrons, even if some of them are shared. Noble gases don't want to share with anybody, so they kind of break the rules. Okay, going down, our electronegativity decreases, which means they're not pulling the shared electrons as much. And here's the argument. As we go down a group, we keep adding energy levels, right? Adding rings, so we get bigger and fatter, more distance between the valence electrons and the nucleus. So because that atom is bigger, there's less Coulombic attraction, which means it's harder for the nucleus to attract the shared electrons. So if I'm big and fat, it's harder for me to attract the shared electrons because the reality is those shared electrons are now farther away from the nucleus. So here's the trend as I move across the periodic table. Electronegativity increases, right? Those atoms hog more, they attract them towards themselves, and as we go down, because we get big and fat, it decreases. So the least electronegative would be big fat francium. And the most electronegative would be fluorine. Why is it not helium? Well, remember, those noble gases don't apply. So I'm going to cross those off. They break the pattern. If it was just based off the pattern that we increased to the right, helium would be the most electronegative. But remember, helium won't bond with anybody, so technically there is no electronegativity. All right, so I got some pictures here. And I want you to be able to see which one of these, A, B, C, or D, is showing what the definition of electronegativity. So the first one, here's an atom. We got the protons. We got an electron. Another atom, proton, electron. So they're talking about this arrow here, electron to electron. Well, we know a negative electron is not going to like a negative electron. So this is really electron-electron repulsion. There's no attraction there, so it's not A. Let's look at B. We have 2 atoms, and a nucleus, and electrons, and it looks like there's some overlap. So these are shared electrons, and we're looking at the attraction from the shared electrons to the nucleus. That looks like electronegativity. We'll check the others just to make sure. Letter C, I have proton to a proton, right? The nucleus to the nucleus. Well, those are going to repel. Positive does not like positive. And the last one, we have another electron and we have another proton, but notice this electron is not in a bond. It's orbiting the atom that it belongs to. This is just a picture of Coulombic attraction, right? Attraction between the positive and the negative charges. So this is my Coulombic attraction. So not here, not here. So B is the best answer for this question. Which has the highest electronegativity, oxygen or sulfur? So we're going to go through the same idea. So it's going to be energy level or rings. And then if necessary, we can look at protons. So highest electronegativity is going to be pulls shared electrons most. Right? Or we could say high Coulombic attraction, because if it has high Coulombic attraction, it will pull the shared electrons the most. So let's look at our periodic table. Got mine pulled up right now. That's a lie. I don't. ptable.com. There we go. All right. So we have oxygen, who is in the second period, and sulfur, who's in the third row or third period. So I don't need to look at protons because it is not a tie. So which one of these will pull the shared electrons the most? Who will have the highest Coulombic attraction? That's going to be oxygen. Here's why. Oxygen in second energy level, sulfur in third. Oxygen has less distance between the shared electrons and the nucleus. So oxygen has higher Coulombic attraction. This means oxygen has higher electronegativity. And we know that electronegativity is that attraction between the shared electrons and the nucleus. All right, you try this one. It's phosphorus versus chlorine. Pause the video, and I'll be back in a second with the answer. All right, so I looked at phosphorus and chlorine. Both were in the same energy level, so I said both P and Cl in the third energy level. So then I looked at protons, and let's do this. Phosphorus has 15 protons, chlorine has 17 protons. What does that mean? Well, it means chlorine has higher Coulombic attraction between the protons and the electrons, which means chlorine has more attraction to the shared electrons, which means chlorine has higher electronegativity. Notice that definition right before the final answer. All right, the last one is electron affinity, and we explain it the exact same way as electronegativity. That's why I kind of group these together, but the definition is what's different. So electron affinity is the change in energy of a neutral atom when an electron is added. So basically, I'm taking a nucleus. I got my neutral atom, so let's say we got maybe a few electrons hanging out. What I'm doing is I'm taking another electron and I'm forcing it into the atom, okay? Usually this element or this atom's going to be in the gas form, but the main idea is what we're doing is we're seeing, is there a release in energy or do I have to use energy to force this electron in? This part gets a little tricky, high and versus low. So here's what I kind of want to talk about in blue. If we measure electron affinity and it's exothermic, which means energy is released, and we usually have a negative number associated with that. This means that the negative ion, so once we've put the electron in, that negative ion is more stable than the neutral atom. And the more negative this number is, so the more negative the electron affinity is, that means there's stronger nuclear attraction. So like basically this guy wants an electron. If it's endothermic, that means energy is needed and it's going to get a positive value. So this, if you have an endothermic electron affinity or a positive electron affinity, that means the nucleus is not effective at attracting an electron, and we had to force it in. We had to shove that in there, so it does not want an electron. It's not happy about it. The reason I jumped to the blue is because that's kind of confusing. Like high electron affinity is actually referring to exothermic, which is a negative number, and low electron affinity means we don't really want that electron. It's a positive number, endothermic. So you're better off just kind of thinking about, yes, it wants the electron, or no, it does not want the electron when it comes to electron affinity. All right, I'm not going to repeat this explanation, but it's basically the same thing as electronegativity. The only real difference is it's not attracting a shared electron. It's basically like, here's my atom, and I want to add an electron to it. Well, how does my nucleus do at attracting that electron? So it's not, that electron is not necessarily attached to another element. We're just adding a lone electron. And measuring the energy difference when that happens. So same idea, if we go across a period, right? I'm sorry guys. As we go across, we have the same number of rings, but we keep adding protons. What does that do? That adds Coulombic attraction, which means it's easier for the atom to attract an electron. So this would be exothermic. But again, you're just able to tell me, yes, this nucleus would attract that electron. As we go down the group, we start to add rings, so we get bigger and fatter. More distance means less Coulombic attraction, means it's harder for the atom to attract that electron. It is endothermic. We have to actually force the electron in. All right, so as we move to the right, this blue arrow, the electron affinity increases, which really means it's more exothermic, which is a negative number. Again, I know that's confusing, but basically what we're saying is fluorine, just like the high electronegativity, it really wants that electron. Okay, and then as we go down, our electron affinity decreases, which means it's more endothermic, more positive. Really, to help you remember, big fat francium does not want the electron. We have to force it in there. Okay, notice I skipped the noble gases because they don't want to give, or they don't want to take any more electrons at all, so they don't apply for this pattern. All right, I want you to try this problem. Pause the video. You'll go about it the same way as you did the electronegativity. All right, so here's what we kind of compared. Fluorine is in the second row, second energy level. Iodine is in the fifth. So we didn't even need to look at protons because fluorine has a shorter distance between the nucleus and the electrons, which means higher Coulombic attraction in fluorine, which means it will accept that added electron. It will release the energy, which means it will have the highest electron affinity, which is actually the most negative or exothermic. All right, last problem. This will be the moment of truth. Can you get this one correct? Pause the video and then check your answer. All right, hopefully you got bromine as having the higher electron affinity, and you can kind of skim through my justification. Those black bullet points are what we'll be looking for when we say justify your answer.